All right. I will be starting now, and while other people are joining, so we will be starting with the introductions. And it will be from me and Jawad. So um, all right. So this is a second session of our workshops for the chiplet design with the 3D IC packaging. It is a joint OCP and JEDEC workshop. So we had a first session last week, Friday, and this is the second Friday. So we have a lot of fantastic speakers from last Friday, and we also going to have more exciting and well-known speakers to present this week as well. We're going to be introducing the speaker for this week in a moment. And welcome for this everyone for this second part of the OCP JEDEC workshops. So Jawad, are you there? You want to start?
Yeah, sure. So welcome everyone on behalf of ODSA. We are basically evangelists for open chiplet economy and are helping the industry build various pieces for that puzzle. That includes design automation, standardization around it such that not only the input of the developers of EDA comes into picture, we also get input from designers and manufacturers and bring all of that together. And our big goal is to get to an open marketplace. And you will hear some exciting announcement on that in a couple of days. We made decent progress on launching some of the commercial platform for that. So we are generally divided into three different areas. We do focus quite a bit on the business and application. And about 2 months ago, we had a workshop very similar to this one, where our focus was primarily business opportunities. And in this workshop, we are focused on design automation, especially in the context of advanced packaging to enable the chiplets. That's the big goal that we got. And in a bigger scheme of things from OCP, there is a push at the moment for AI. And to enable AI, we originally in ODSA, we were focusing on domain-specific ASICs and accelerators. So that has a life of its own now. It basically progresses in the form of domain-specific chiplets coming together. And I'm sure you're aware of bunch of wires. That is a standard that we put out some time ago, CDX, a chiplet design exchange, where we are putting some of these collaborative standards in collaboration with JEDEC in particular for the industry, which is the foundation of some of the talks that you are going to hear today. And we are in general agnostic to one single manufacturing line, the reason being that we are open, and our bigger goal is generally to help the industry, and that's where we come from. And what you will see today is primarily around the design and the modeling piece of it. Do join us for modular chiplets. We have a pretty exciting new work stream going on in high performance computing. We are progressing on a variety of bunch of wire follow-ons. And then there is obviously some work that you will hear about in the memory space. So that's the big scheme of things. So James, I think that's all from me. If you are interested in joining us, go to groups.io and search for OCP-ODSA, and you can pick and choose what is your area of interest. We do cover interfaces, design tools, and business opportunities. So they are basically broken into 3 different areas. Join us. We have a session at Lawrence Berkeley National Labs on Monday. We also have a session on Tuesday at Design Automation Conference. And do watch out for another workshop like this that would be focused more on the interfaces side of things, and that would be another couple of months. James, all yours. James, you're on mute. We can't hear you.
Oh, yes. Thank you, Jawad. As Jawad pointed out, CDS is just another work stream under the old ODSA or Open Chiplet Marketplace. So we're focusing on the standardizations. So that's why we have this workshop, and we like to hear about from everyone from the industry about the challenges that they're facing in the business regarding the standardizations, especially in the 3D IC design and also the chiplet, where they are getting to more like plug and play and a lot like sharing resources. So and we definitely to hear like more from you about the challenges today. We already have the CDSML, the standard, which is incorporated with the JEDEC part model, JED30. We're also working right now on the material design and also assembly design, and also like the testing design kits. This is a program from the last week, and I would like to introduce like the program for this week, which is like we'll start with the Lalitha from Intel, and then we will have David Ratchkov from Anemoi software, and then following that we're going to have a panel title from the Synopsys. We have a Dominic Brown from ARM. We also have the government agency feminine representative Farah Fahim, and then we will have another like company microchips Anu Ramamuti, who is also an OCP colleague. And then for that, we also have an educations of UCLA's who Puneet Gupta will be presenting. Following that, we're going to have like Alpha Summit where Su Fung will be presenting, and followed by another standard body SI2 Matt Ross, who is also like participating in our OCP the 3D IC meetings. And then lastly, but not the least, we have Aaron from the Blue Cheetah. He's also another colleague of the OCP. He's a great presenter, so we will excited to hear from him from his perspective. And then I will be doing a short crossings at the end then. So this is kind of quick program for today. And quick rules about the presentation today is like 15 minutes for every speaker. We will give a reminder at the end. That's it. Like we'd like to start with Lalitha. If you are ready, please feel free to share your screen and go ahead and start.
Hopefully you all can hear me.
Yes.
Yes. Okay. Thank you for the opportunity. I'm Lalitha Immaneni. I work in the packaging organization at Intel. Today, I'll share my perspective on when you are looking at these heterogeneous integration of chiplets using the advanced packaging, whether it's your 2.5D or 3D or whatever the packaging technology is. How do we make the design enabling aspects happen where every company doesn't do its own customization and its own design enabling aspects. How can we come together as an industry by driving some standards and also by driving some of the much needed integrated CAD agnostic flows within the EDA industry? So again, we'll show you a foil on 3D IC design, what's different about the landscape, what are some of the challenges that we face as we are embarking on the design enabling of 3D IC, right? Not just from the aspect of layout execution, but also coming up with optimum architectures, and then what are some of the key building blocks and standards needed in the industry amongst all of us. So heterogeneous integration, this is the place which is driving the next era of Moore's law. Just by means of breaking these big die complexes into chiplets and leveraging packaging, I think I heard a bunch of wires. There is also high-speed chip-to-chip interface like UCIe, putting the memory together, looking at the custom IP and chiplets. How do we bring it all together without blowing up the cost of the product and also meeting the much needed time to market demands, right? So heterogeneous integration is the one that enables the construction of these complex SoCs that are exceeding sometimes the max reticle sizes, right? It gives you an opportunity of bringing in the chiplets from various process nodes together. It doesn't need to be from one foundry. Faster time to market by enabling some reuse of chiplets, reuse of the IP. It enables optimal process technology as it breaks up the dies, the chiplets. There is a better yield option. It also reduces the IP porting costs because now you're going to look at certifying these die-to-die interfaces for various packaging technologies, and of course, hence lowers the SKU cost. I am from the packaging area, so very happy to see how prominent packaging has become in the industry. What's different about the landscape, right? I mean, I have been on this journey since we probably did lead frame designs. I'm sure a lot of you don't even know what that is. Those are like the 40, 60 pin count packages, right? On towards the wire bond, the FCBGAs, the bridges, the interposers, and the hybrid bonding, and so on. The landscape is, I want to say, 100x complex than what we used to deal with. The co-design, the point at which when the complexity is not as much, we did do some amount of co-design between the die and the package and the board, right? Co-optimization across the deck. That has become way more complex. The products are now getting architected through a mix and match approach. I can bring in different dies from various foundry processes. They can be designed by multiple design houses, right? And then depending on where you are assembling it, you are now going to deal with various assembly constraints from different foundries and OSATs. There is no such luxury that I would do a complete 3D IC architecture execution in one EDA tool. I think various EDA tools are very good in some particular areas, right? Some in design execution, some in co-design, some are thermals, mechanical, signal integrity, power delivery, final verification, and so on. So there are multiple EDA tools here. So it's truly a combination of IC and packaging design tools. Doesn't mean somebody just designs these chiplets and throws at the packaging and says, make it happen. There is a whole lot of co-optimization that happens, right? Early risk analysis during 3D architecture definition becomes much more critical. And I think that's what is really different about the landscape. The complexity is more emphasis on coming up with optimal architectures. Way before you get into an execution phase, you need to know, hey, am I meeting the performance criteria? Am I not? I need to make sure that the pack costs are less. How am I going to test this whole system? So that's where, the chiplets with the advanced packaging portfolio on towards really generating products, the landscape warranties a different kind of mindset in the industry. So what are some of the challenges, right? Disaggregation strategy. How do I partition? What silicon nodes do I pick? Die-to-die IP, which die-to-die IP? You mentioned several names, right? Is it UCIe? Is it certified on a bridge or on an interposer? What are the bump pitches, decoupling capacitance aspects I need to worry about? What packaging do I need to choose? This phase of planning is where I think there is, I have to say, this has been a pitch I have been doing in the past, I want to say like a decade. We have come some ways. I think I have to thank the EDA partners that we work with. They have come a long way in terms of putting together some co-design planning systems, some great multi-physics changes have happened in dealing with the complexity and scalability, but still, there is still a lot of customer engineering. We really want some kind of a 3D IC design enabling kit that comprehends the technology aspects and gives us a reference flow so people can use it. I think we need to compete on, coming up with optimum architectures, not on the standards. So the emphasis on increased trade-off analysis also increases. So how do we achieve, maximum flexibility and design productivity without impacting the timelines? So this is what I think should happen, right? Right here to the left, I'm showing an example. I think this is PVC. Look at it. It has 47 pieces of silicon in one package, 3 foundries, 5 silicon nodes, and you're looking at the transistor count, fairly complex. So to enable a lot of things like this, whether it's an AI or an HPC, segments or even co-optics, for instance, we need to have a very nimble co-design system that drives integration amongst the die package and board design tools. The design kits should have an end-to-end focus. We need to stop paying much more myopic attention to each area. At a holistic aspect, we need to know that, hey, even before I start doing my floor planning or taping in the package or the board, I need to know that I can come up with an optimum architecture bearing the signal integrity, power delivery, thermals, warpages, and what form factors can I even afford? All those trade-offs need to happen in this co-design system. And then comes the burden on the ecosystem and standards. All the standard IPs, whether it's a bunch of wires or UCIe or anything else, they need to be validated and standardized for the packaging technologies that are being leveraged within the industry, right? This can be die-to-die, this can be off-package IP, advanced packaging, and EDA should really move to CAD-agnostic standards, right? Chiplet standards. I should be able to go look at a chiplet and bring it in, and maybe it might sound like utopia. Hopefully we'll get there, being able to mix and match these chiplets with packaging, right? This is where putting together a co-design framework, interoperable, tools, flows, and methods, and file formats, data exchanges, and workflows. We all tend to always jump so much into, multi-physics and how complex the overall system is, right? You are truly looking at STCO, the system technology co-optimization at this point, but a workflow tends to become much more critical. as you are looking at, large databases and simulations. So standards plus a very strong ecosystem, CAD agnostic formats, and a framework where I can pick, any ADA tool that I want for my application, and leveraging co-design flows, which kind of embed the process / packaging / PCB offerings that I can play with, tends to be very, very critical. I think that's all I have. Thank you for the opportunity. Again, if there are any questions in the chat, I will make it a point to respond there.
Yes.
Thank you so much.
Thank you, Lalitha, for the wonderful presentations. We get a lot of insight, I think, especially from Intel's perspective, and then how critical and important about these standardizations. So I think that's why we're all here, and hopefully I think we will learn something from this meeting and have more cooperation and to strike towards to come out. I think these standard formats, I think I will benefit everyone. And yeah, and we look forward for others and participants and speakers, I think to their intent as well.
Thank you so much.
Thank you again. And for everyone else, feel free to leave your message in the chat, and we will try to answer them. If we don't get answered, we always follow up after the meetings, and we will post that on the OCP website. For the next one, we will have another great speaker, David Ratchkov from Anemoi. David is also in co-lead for the CDX. It has been a great contributions on the road standard as well in this year. So let's hear from him on his perspectives. David, that's all yours.
Thank you very much, James. Is my audio coming through okay? Is my presentation visible?
Yes, we can hear you. We can see your presentation.
Okay, perfect. Thank you very much. And hi, everyone.
You want to do a slideshow?
No, I'm actually going to do some interactive tool switching.
Okay.
Instead of doing slides, I'm going to show you live tools, some eye candy. So a couple of things. I'm the CEO of Anemoi Software, but I also am co-lead of the CDX work stream. We work in a couple of areas. We work on design kit. Our first white paper was on chiplet design kits. And further down the slides, I'll show you live implementation of some of those design kits. Second thing we work on is workflows. And I will show you some of the things that we have done. And I have some cool announcements. But before I go into the actual slides and show you actual tools, really, when you're dealing with chiplets, you're going to be doing a lot of top-down thinking. Right, you're going to be thinking about, are my chiplets electrically compatible? Are they mechanically compatible? What technology would I use for my substrate? How would the whole thing work? And really, the problem starts with, okay, I have a chiplet. Where do I find more chiplets? For that, we have created a marketplace. This marketplace is enabled by CDXML, where chiplets can be defined and published. And the bare minimum is just tell us which part of the CDK model you would provide. I'm happy to announce that this is open now. So if you are in the chiplet business and would like to publish your availability for chiplets, we would like to work with you. And let me show you how it actually looks so that you know. Here is our website. And most importantly, we have a catalog of chiplets. There's standard chiplets and custom chiplets. But if we look at some of the interesting chiplets, here is a IVR from a partner company that supplies integrated voltage regulators. Another cool example is an HBM3, which was this model was created by Palo Alto Electron, and you can see we have all the details for the HBM, and you can come in and actually use this, right? And you can publish. So again, please join us if you're interested in this. It's straightforward, it's free, and we would like to work with you. This is where the top of the ecosystem is, right? The availability of chiplets and the ability to find and integrate them together. Next, you're going to be working with several different things. One is one of the most important pieces of data that you would need are the what materials are you going to be using, especially for your substrates, any attachments, things like that, right? You would need to work with materials. So for that, we have actually created at Anemoi Software a material design kit that looks like this. It's free to sign up here, and you can create your own libraries. The coolest part of this is you can actually share this with friends, right? So one of the most difficult pieces in materials is that you always have to go and dig up a PDF file and then pass number by email to somebody and try to enter it in a tool. This kit here would allow you to just share the materials. And most importantly, if you use the material and you change something, we can warn you that something has been changed, right? So you are on top of any changes and you don't use any stale numbers. So material, James and team have been working on refining the definition of material, of what's in the material design kit. And we are implementing those changes. So again, this is open to Chiplet.us members. It's free. We would like to enable everyone to use same values, right? And so that we can reduce any possibility for mistakes. Next, when you're looking at top-down system, you are going to be looking at the physical aspect of this. How do I place these things together, and what will happen when they're together? What would my thermals look like? What would my mechanicals look like, right? Would that work together at all? Can I place them? And for that, I'll show you a live demo of the same tool. Here is a simple chiplet system that was designed, right? We can look at the Z heights, we can look at the BGAs, we can go and create that very easy. Again, this is standard file input output. So even if you come in and just create this, you can always get standard ECXML out of this, and then you can go into any other tool which you want. Again, open standards are the key for open chiplet economy. So we are determined to support those. And then you can look at the thermals from different points of view and see how things are coupled thermally, where the hotspots are, how the heat is propagating to other components, and so on, right? You would get different components with different ratings, especially probably the best example are memory modules, which would have different rating than the standard ASIC. So you need to be concerned about how heat is propagating to those components, and then figure out the rest of the system, right? What does the heat sink look like? What would serve my thermal target, right? And look at the BGAs and so on. So okay, switching gears again. I have very limited time. I wanted to talk about the other aspect of this. Okay, so we can get chiplets, right? We can take a look at the available chiplets. We can take a look at the 3D system, but how do we create chiplets, right? How do we insert our chiplets into the system? And for that, excuse me, really, again, this is a top-down approach where you would come in, you would define your system. You can create your system netlist. You can create your system supplies, power supplies. You can create your system power vectors. What is on, what is off. That will give you immediate feedback on total power. And total power includes all chiplets in different states. It would include any IVRs, everything, right? One of the underappreciated aspects of this is the power losses on the IVR and calculating those for a specific vector. That's not easy today if you're using PDF files as your source. Instead, we have electronic model that can automatically compute your losses depending on what the power vectors are on the loads, right? Basically on the different chiplets. You can take a look at your system power, and then most importantly, you can take a look at every chiplet. What is the power distribution map, and take that into thermal simulation and see both spatially and temporally how heat propagates to that. And here's the same life example that I was showing you. Here is my system with the CPUs and the HBMs. Here's my power vector that I have defined that I'm looking for power for it. Here's what my supplies are doing, right? Depending on if you would be doing DVFS, no question about it, right? But specifying what are the voltage levels at different points in time is important. Then you can take a look at what is your netlist, right? Creating netlist, the standard way to define a package connectivity is Verilog, and creating netlist for hundreds of thousands of nets by hand is a crazy proposition. So instead, we have automation that would enable you to actually take a look and create the netlist in a very few commands. In this case, as you can see in a few commands here, we'll be able to create the top level netlist for the HBMs and for the CPUs. And then having that netlist, we'll take a look at what the power is. And here, if you take a look at this, here's my power distribution map for this chiplet. Here's the power distribution map for the other chiplet. Again, if you notice, the power density is different in the two cases. That's because the two chiplets are executing different power vectors. So this is one aspect. Okay, so we have defined, right? We went top down. We looked at what the chiplets are. We looked at the mechanical. We looked at thermal. Then we defined our system. Then the next aspect is, how do I go inside the chiplet and define that? And for that, as continuation of the same cockpit, you can actually dive down and define your full hierarchy of the chiplet, define what your floor plan is, define what your chiplet level power tree is, then define the modes, and actually look at the path design as well. All of that comes into one cockpit that would enable you to go and define chiplet like this. Here is my CPU chiplet that I was just showing you. Here is the floor plan for this chiplet. All the instances which are in there. You can see we have bow interfaces on the sides. We have the CPU cores in the middle, and we have the HBM5 on the side. We can define any power for the top level chiplet. Again, the lower level chiplets, the lower level blocks in the chiplet, power is going to come from the model for that IP, that particular IP. We can take a look at the power operation, the mode of operations for this chiplet, what it does in different states. This gives us the high level representation. We can take a look at supply connectivity, right? Which supplies, which IPs in that chiplets are connected to which supply, so that we can generate correct per supply power and current waveforms for every vector. Part of the CDK is being able to provide, right, to generate the substrate level netlist, you would need the pin definitions. So we can handle the Verilog. All that comes from Verilog. And then the Verilog, at least the boundary Verilog. How much time do I have, James?
You have 1 minute remaining.
Okay.
Yeah.
Okay, so we use the boundary Verilog standard part of the CDK. Then we can come in and define the bumps where they are. Again, this is in fully hierarchical fashion, so you can move things around. So this is our cockpit, and actually perfect timing. So again, we are committed to enabling the open chiplet economy. There's a lot of top-down work that needs to happen, and we want to enable that work to happen in electronic format. No need for PDFs and emails, right? All this needs to be in electronic format, and not really share the some design file with other person, but actually share the actual a live design with another person, so they can come in and review it and suggest changes. Thank you. And if again, Chiplet.us, we definitely would like to see you join us. If you're working in the area of chiplets, if you have IPs, substrate technology, assembly technology. Oh, did I? Okay. One last thing I wanted to mention before I go. We have a library that feeds into all of this, that covers what silicon technologies are there, what package technologies, heat sinks, IVRs, what assembly rules are there, and also the materials used for different pieces of that chiplet definition. Thank you.
Yes, thank you, David. For great presentation, and I think I shown us how the CDXMLs and other standard the MTK that has been incorporated in the tools. So we are looking for more. I think this kind of activities. I think that will be benefit everyone. So next we have another. Sorry, we short of time, but feel free to ask your question in the chat. We will definitely answer them when we get the opportunity at the end, or if not, we will post them online on OCP website. So for the next presenter, we have Aparna Thader from Synopsys, another EDA firm. We listen to her from her perspective. Thank you, and Aparna, it's all yours.
Thanks, James. Hi, everyone. Good morning. I am Aparna Thader. I work as a technical program manager, product manager, sorry, at Synopsys. And I will be talking today about enabling our multi-die design with Synopsys UCIe IP and 3DIC compiler. The technology trends today are evolving so fast, and we are having a huge boom in AI applications. And the SoCs today need a lot of bandwidth and all the functionality embedded into the single chiplet, which has maxed out the reticle limit, and of course has pushed us into the era where system on chips has now become system of chiplets, as I say it. This has also evolved our packaging technologies that I try to summarize here with the 2D standard packaging, and which has always been super popular with organic substrate. And it has also moved on to increased IO density and count, where we have technologies in 2.5D and advanced packages, right? RDL fan out, silicon bridge, and silicon interposer type of designs. We have then also moved on to hybrid bonding with 3D stacking of dies now, which has led to even faster connections between chiplets. This has also produced a need for high performance die-to-die interconnects, and which has been defined by different standards, especially UCIe standard specification has defined the whole stack of protocol layer to data link layer and the PHY to try to solve this problem. Synopsys has a UCIe IP solution where we do provide the complete stack from protocol layer, die-to-die adapter, and physical layer. We provide interfaces to the SoC side for AXI, CHI chip-to-chip, as well as CXSB coherent interfaces. We provide protocol layers for PCIe as well as CXL. And we deliver a complete stack of solution from PHY controller to the verification IP. We also have designed for test utilities, as well as emulation and signal integrity, power integrity analysis. We have the 3D IC compiler to help with packaging that I'm going to talk more about in my coming slides. And we also have subsystem services where you can have the whole system designed and tested for your applications on the dies. So we have been used to the traditional flow of die design, like a single chip, where you have the architectural specification, you have to design, verify, synthesize, floor plan, power plan the chip, create placement and routing, and then of course have the DRC and layout versus schematic tested to sign off the chip. This is all related still when it comes to advanced packages, and when multiple chiplets are connected to each other, you have to follow similar kind of steps, but on a package level now, to make sure your die-to-die connectivity is going to work as you have defined it and going to meet your matrix for specification, right? So you have to make sure that the placement and routing of the dies is good. The architects need to architect the placement and create the routing. You have to make sure the inter-die routing and placement is good, as well as the package and interposer talking to outside world. Those connections are met. You have to extract the parasitics and perform power and signal integrity analysis and create sign-off tests for the package level itself. And thanks, Lalitha, for your presentation. You went through all those challenges that are involved in all the whole process here, and there are a lot of different engineers involved, different teams with different expertise, from package design, layout, connectivity. Everyone comes together to hold this tremendous task, push it out of the door. Our Synopsys 3D IC compiler tries to optimize these tasks and automate it and help this process to be very smoother as respect to the design flow, right? The 3D IC compiler takes multiple die inputs in the form of LDA, NDM, LEF, DEF files. It takes the bump maps for different dies and IPs, and then tries to create a unified flow with the NDM database, which then can be used like for an advanced package, like with an interposer. You can initialize, give parameters for the interposers, then initialize these dies on the interposer, try to connect them. You can add dummy dies if your design needs to, and then you can export parameters from this whole layout, which our HFSS tool tries to extract the S parameters, extracted models, and these can be used as an input to the HSpice tool that Synopsys has to run signal integrity, power integrity simulations on the whole package, so that you can look at if your design matrix have been met, if there are any hot corners or routing congestion inside the package anywhere, and try to resolve those issues early on and try to mitigate risks early on in your design cycle. This is one of the snapshots from our UCIe IP interposer design layout, where the 3D IC compiler is capable of doing automated routing throughout the package. And this is one of the automated routing snapshots of the compiler. And it does the sidewall shielding as well as interlayer shielding as well. It achieves 100% routing density with custom shielding patterns, and boosts the package design productivity a lot. As a conclusion, I would like to note that for our UCIe IP deliverables, we run through, we not only test our GDS for the IP as independently, but we run through this whole flow of trying to package it together inside an interposer package and try to see if everything is meeting the design expectations. We deliver the compiler scripts that are required for IC validators sign-off flow. We also deliver the interposer design guidelines. We have the S parameter models for signal integrity analysis that can be used for signal integrity simulations. We have, of course, the IBIS models with the UCI PHY, and we run and deliver the power integrity, signal integrity analysis so that customers, when they embed our designs into their whole SoC, have something to compare to and see, what design matrix and margins can be met with respect to the IP, and try to resolve the overall system productivity with it. With that, I would like to conclude my presentation. Thank you, OCP and JEDEC, for this opportunity to present here, and you can reach us out on our website if you're interested. Thank you.
Thank you, Aparna, for great presentations.
Thanks.
And we we do have a few minutes, right? And thanks for the full speed presentation again from Aparna. Anyone have any question? Feel free to ask.
Yes, please.
I saw in the chat, I think, Renlin, I think I asked earlier about the manufacturing foundry, which manufacturing foundry has been part of this OCP open system. So we do have many participation. I think from the foundry, I think Intel has been participating in our some of our meetings. And we definitely look forward, I think, for more people, I think, to join, right? And besides foundries, we have many others, like EDA companies. I will also have, right, the assembly side company, right? Yeah, hopefully that's answer your questions. And we have
I have a question for
Yes.
Aparna. Do we have a minute?
Yes. Hi.
Yeah, okay. So Aparna, what is your opinion on interoperability certification for some of these die-to-die protocols?
I think what we try, especially at Synopsys, we have interoperated with different vendors, like, in fact, our UCIe N3E chiplet was the first industry standard that interoperated with Intel UCIe. These were heterogeneous chiplets on the same EMIB package that Intel has. And it was Intel's UCIe IP that they designed. It was Synopsys UCIe IP we designed. Ours was on N3E, and Intel's was on a different node, Intel node. Ours was with TSMC, and they both interacted with each other in the single package. And, it was a big deal. And I think this is what Synopsys tries to do with respect to open chiplet ecosystem. And we try to interop with different vendors that deliver the same IP solution, right? And if UCIe specification is taken into account, we have they have a standard called the golden die, which would be really used for compliance, that would that would help to make interoperability define more accurately as well. But I do think different vendors interacting with each other is how interoperability would be defined for a die-to-die, right? Does that answer your question?
Yes, great. Thank you.
Thank you.
Yeah, thank you again, Aparna. We have next speaker, Dominic Brown from ARM. Yeah, Dominic, when you are ready, please go ahead and share your screen and begin.
Yes, second. Can we see?
Yes, we can see your screen.
Good, good. So yeah, so my name is Dominic Brown. I work at I'm a engineer in the architecture and technology group. So I'd like to talk today a bit about ARM's approach to reusable chiplets. Now, I think we all have seen a diagram very similar to this multiple times. So you know the different phases of having a chiplet ecosystem. There's obviously proprietary chiplets on the left, and then on the right hand side of this diagram we see you know, the idealistic multi-vendor chiplet marketplace with lots of different standards and everything that sort of all work together to be able to create plug and play chiplets. But we're not there yet, but we are approaching an area where we, you know, potentially have multi-vendor different chiplets being mixed, and we have a requirement obviously for protocol transport and PHY standardization. So what's ARM's approach to trying to drive this ecosystem forward and its collaboration? We have sort of three main areas. One is our protocols. Obviously ARM is famous for its AMBER protocols, which are used widely on system on chips. We are extending those protocols to chip-to-chip interfaces, and you know, to enable that sort of standard interconnect ecosystem to proliferate with chiplets. We're also looking at the partitioning of chiplets from an architecture perspective, and trying to bring consistency in that partitioning and interfacing to ARM-based chiplets. And I'll go a little bit more into these initiatives in a few minutes. But one of the important ones as well is collaboration. So ARM's all about collaboration. So we're not looking to rewrite the rule book here. We are into, you know, collaboration with existing standards and reusing and integrating as much as possible to you know, the ecosystem standards wherever they exist. So when it comes to the AMBER protocol for chip-to-chip interfaces, so we're extending we have the AMBER CHI interface, which is an on-chip standard for coherent interconnect, and we are extending that to CHI chip-to-chip, which is a way of taking the on-chip CHI and packing it in a way that it's easy to send over chip-to-chip links. And the interface is layered such that obviously the CHI protocol and then the chip-to-chip packetization and then the physical layer are all layered such that we can interact with different standards here. So there's no sort of linking with any particular standard way of propagating across chips. So we're open to all the standards that exist for those purposes. I mean, the advantage of having a particular CHI chip-to-chip protocol is that it avoids conversion between CHI and other standards that might be used for cross-chip protocols. So there's less latency when it comes to doing that, and minimizes the complexity of that. And obviously, for streaming interfaces, there's things like UCIe, which is fully supported by the AMBER CHI chip-to-chip. So one of the other major initiatives that we've started is the ARM chiplet system architecture. So what we are seeing is that obviously the ARM ecosystem wants to use AMBER to use across chiplets that are used to build SoCs, which might traditionally have been monolithic, but those interface protocols alone don't necessarily provide a full opportunity for being able to reuse a large number of chiplets, because if people just have a way of connecting via a protocol, they may choose different partitioning choices, and that could lead to fragmentation, which when it is needless differentiation can just end up costing everybody within the ecosystem. And similarly with UCIe and CHI chip-to-chip together, they're necessary, absolutely necessary pieces to the story of making chiplets reusable, but they're not sufficient to fully enable an ARM-based system with reusable chiplets. So our initiative is the ARM chiplet system architecture, and the idea here is it says here to constrain partitioning choices, but it's more about defining those partitioning choices such that we have a reasonable subset of chiplet types that we can have to try and enhance consistency and compatibility. And one of the important things here was looking at this partitioning on an architecture level. So we're looking at what functionality needs to be in the different chiplets, and that obviously leads to questions about what the interface needs between the particular chiplets are, because those different architectural pieces need to communicate. And one important factor here is that we're not trying to create any new industry standard like UCIe or PCIe for any of this. We are referencing industry standards that already exist. Obviously, that includes UCIe, includes AMBER CHI chip-to-chip, which is an ARM standard, but it's an open standard that anybody can access. So we're not trying to recreate anything here or drive anything different that's proprietary. We're just about trying to increase the consistency of chiplets designs across the ecosystem so that it can better work together, so that our partners can concentrate on providing the differentiation which makes their particular functionality special. So we see the benefits as reduced risk, cost, time to market, and making consistency in chiplet type design and interface choices. We want to increase compatibility and opportunities for chiplet reuse, so that we can provide the commodity parts while allowing people to concentrate on the valuable differentiation. And I think we see the ecosystem where people can reuse many different chiplets and chiplet types could lead to a lot of innovation for different combination of chiplets. So what's the vision? So as I say, we're partitioning an ARM system. So the first thing is we want to define chiplet types, classify them, their properties and functional requirements, and then establish a common language so that people can talk about different chiplet types on different systems and have the same meaning when they talk about particular types of chiplets. And then identify the system level chiplet interface and requirements and how we would achieve those. Obviously, interoperability is a major goal. We want to create consistency, and we want to enable the differentiation, and that can be done with this consistency because you don't have to focus on all the parts which are everybody wants to provide, and simplify the chiplet specification and integration. And we're not claiming that this covers all the bases of chiplet specification and integration, but it covers the parts which say what functionality should you have in each chips and what's the most likely way you want to interface them, so that eases the path to integration of chiplets and other standards which are used to attach at different levels. And reuse is obviously a goal, as we've said. There's obviously going forward, there's going to be, as technology develops and different types of chiplets are developed with different technology going forward, there's going to be intervention versioning and compatibility, even when it comes to standards, what things can work together and how do they do that. And one of our sort of key sort of aspirations, I guess, if you like, is that we can specify enough such that somebody is able to develop a chiplet standalone and that to be able to work with other chiplets which are also developed standalone. Obviously, as many people have discussed in these presentations, there are a lot of issues with that on a lot of different levels. We're not trying to solve all those here. We're looking at a particular sort of subset of the functionality and the architectural functionality that goes into those different chiplets and trying to provide consistency there. So what is the chiplet system architecture in an overview? So we have a specification of different chiplet system types. So the idea here is we've taken a view of what we see as market requirements, some of our partner feedback, and our own internal perspective of what we think are feasible chiplet technologies. And we've tried to use that to create a system, how a system would look with the combination of chiplets, and make good choices about where those different things should live. Now, some of those are driven obviously by sound technical choices and the reasons for having chiplets, such as, you know, technology decisions and yield and reuse, and other things. It's more about just providing a consistent way of delineating the different chiplets so that people put the same things on the same chiplets so they can more easily work together. So once we have these system types, we specify a set of chiplet types which are based on those systems, and we provide a set of requirements that make the chiplet specific for its purpose. So these are reasonably high level properties. Again, we're looking at an architectural perspective here, but there is also, you know, there's a slight grayness there where we need to specify things which are slightly more detailed than we do that. And once we've got the functionality requirements for the chiplet sorted, then that obviously leads to a set of interfacing requirements, because we know the system chiplet topology that we're going to be working with. We know what's going to be in the other chiplets, and therefore how those chiplets need to interface and the interfaces that need to live between the two chiplet types. And again, we're expressing these as high-level properties. We want these to be sort of applicable to a large number of chiplets. We're not specifying a very specific system. We're talking about general topologies of chiplets that can exist. And then what we also do is we have an attempt to map that to actual interface implementation. So going one step further and saying, we think the interface for a particular type of to carry a particular type of protocol should be this. So again, trying to drive standards there, but trying to drive standards in the sense that we are referencing other standards, and we say we think this is the best open standard that you should use for a particular transport or protocol that you need. And then there's obviously, when we talk about the functionality crossing chiplets, there's a possibility that we don't have any protocols that satisfy a particular need within the industry as we have them. So that's where there might be proprietary solutions in the industry, and what we're saying within the CSA is those are implementation defined, and that's useful because it at least identifies where these interfaces.
Dominic, yeah, 1 minute remaining.
Okay, cool. Yeah, so that indicates where there might be something that's remaining that needs to be done, and that might be taken up by ARM ourselves, or we might be driving that within industry standards. Okay, so this is my last slide pretty much. So just looking at typical use cases that we've been looking at in terms of very simplistically the type of chiplet architectures that might occur. So yeah, and just a summary about our system. So I hope I made that within the minute.
Thank you. I think for the wonderful presentations. Since we don't have time, I will move on to the next speaker, but please feel free again, put your question in the chat. We will wait to answer them when we can. And also, I'm posting the link of the day one recording in the chat. Please feel free, to look into it. And then for the next speaker, we will have Farah Fahim from Fermilab. Farah, whenever you're ready, please go ahead and start. And welcome.
Hi, everybody. Okay, let me just try and go to full screen mode. If I can find the right buttons. Okay, can you see everything in full screen now?
Perfect.
Okay, perfect. Okay, so I will give a little bit of an overview from a DOE advanced scientific instrumentation perspective, where we are designing or would like to use 3D ICs and have been using 3D HI for advanced scientific instrumentation, which operate in extreme environments. So we have a few unique challenges, which are, I think, slightly beyond what industry is currently tackling, but something that DOE is trying to address. Okay, so just to kind of set the scope a bit and try and give you an overview of why this is needed for DOE. DOE builds and operates vastly complex particle detector systems to study fundamental physics. And just to show two of these experiments here is one of the experiments at the Large Hadron Collider at CERN, and you can kind of see the scale of the detector compared to a person. There are roughly around 100 different IC designs that have gone into this detector for various different types of sensor technology. And essentially, one of the big things about why we want 3D ICs has got to do with just the sheer amount of data that is generated in these experiments. We kind of create about petabits per second of data, and to kind of give you a rough scale, that's approximately the same amount of data as is generated in the entire internet traffic in all of North America. So that's just one of the experiments that's producing that much amount of data. And if we don't process this data very quickly, there's no means of actually storing this data. And essentially 99.999% of this data doesn't give us any new information. So we are trying to look for these rare events in all this amount of data. So we would really like to, filter and featureize the information and try and convert this raw data into useful physics information as soon as possible in order to accelerate physics discovery. And there are many such experiments that are done for within the DOE complex. To name a few, there are these advanced light sources that are deployed, which have all types of imaging X-ray detectors, which are used for material science and, for example, drug discovery and protein, identifying protein structures and the like. And then, so one of the key aspects of almost all of these different detectors that are out there is that they operate or require custom microelectronics, which operates in extreme environments. So this is either high ionizing radiation and or cryogenic temperatures. And again, to give you a scale of the ionizing radiation, we are about 1,000 times more ionizing radiation than you see in space. And to top all of that, I think most of these detectors, once they have been deployed, you don't have access to the electronics for the length of the experiment. So the electronics that is deployed in these situations have to be extremely robust and operate in these extreme environments for over, about 10 to 20 years without any access to them while they are doing state-of-the-art functions and giving us information which we need to validate very, very quickly. So that's just setting the scale over here. So once in a while, every 10 years, that is, the community, so not just the high energy physics community, but most of the DOE community gets together to come up with what are the next experiments or the next decade of physics or that we would like to focus on. And such an exercise just happened last year, and we created what is called a P5 report, which is a prioritization panel report. And essentially, the report identified that the current detector instrumentation technologies have already pushed the boundaries of sensitivity and scalability to their limits, and new technologies are needed in order for us to be able to cope with the experiments that are being proposed. A similar exercise was also carried out in Europe The result was a table like this, where all these different experiments, which are the experiments that we are likely to undertake in the next 10 years, have been identified, and 3D ICs and high density interconnects have been identified as one of the key technologies that are needed for us to be able to make any progress in the science mission of DOE for the next decade. Okay. So it's not that we did not know about this, right? So DOE, particularly Fermilab, has been investigating 3D ICs for over almost 2 decades now. We started looking at 3D ICs for advanced scientific instrumentation way back in 2006. And we evaluated various techniques, setting the current industry standard for hybrid bonding. So one of the very first few wafers that was demonstrated using the hybrid bonding DBI technique, which was originally developed by Ziptronics and later on licensed and utilized extensively in industry today, was demonstrated on one of these wafers that Fermilab, or some of the chips that Fermilab had designed. And in order for us to do this, what we ended up doing was we created a DOE-specific 3D IC consortium with various university labs and industry partners, including a lot of international collaborators, in order for us to, develop and demonstrate the technology. And the goal was to, kind of create a modular detector system such as this, where there was a large area wafer, which was connected to multiple 3D ICs. The plan was that we would have about 50 of these chips connected at reticle size chips connected to a wafer scale sensor, and the data would be processed by FPGAs. A highly parallel system. We never got to this system here, but we got to an individual module which had a sensor layer and a 3D IC, and we managed to kind of come to a point where we showed decent enough yield. And to again kind of tell you a little bit more about this, we had chips which were about 1.25 centimeters by 1.25 centimeters. It had over 1.5 million signals being interchanged between 2 layers of the chip, an analog layer and a digital layer. The analog layer was primarily doing signal processing. The digital layer was primarily, kind of converting the analog signal into digital information, packaging the information and sending it off to the FPGA to be able to process that information on the fly. Then we did quite a few beam tests, and we demonstrated that 3D HI was definitely the way forward for us. It definitely improved sensitivity. It provided us the speed and the processing power that we needed in order for us to be able to show very complex scientific experiments. And it took us about almost a decade, about 8 years for us to, when we started looking at the various technologies, to show a small module inside the beam and prove that this was, a feasible technique. From there, we kind of fall into this perfect trap of advanced scientific instrumentation that is needed for DOE. Because of the low volume prototyping that is needed, we are in a perfect Goldilocks situation. We are too big for what academia can meet as needs, in an academic fab, and we are too small for industry foundries, big, large foundries, to be interested in pursuing the work that we want to do. And then we end up working with small businesses, and over the past 15 years, having demonstrated about 10 years ago that the technology is very suitable for our applications, and this is the direction that we would want to go to. It takes, a lot of trial and error with companies morphing, changing hands, selling off, changing their roles, and ultimately the technology not being accessible to DOE. And for us, what is super important is this mid-volume piloting and prototyping facility, which allows us to do multi-project wafer runs so that we can very quickly show the different applications. And like I was showing you before, customization is very key to our detectors, because even within one large detector, the number of ICs that are needed and the number of different designs that are need to be demonstrated is very high because of the extremely challenging environments that we live in. Yeah, so again, setting the scale over here, we need this mid-volume prototyping. So we have to do this in like about 100,000 devices, as opposed to the 5-10 devices that academic research needs generally demonstrates, and this billion devices that are typically demonstrated in industry. Okay, so I, again, kind of trying to say what is needed for the next 20 years. We are all the time trying to integrate this sensing, edge computing, and communication in order for us to be able to, not only sense the particles that we are trying to sense, but also correlate information between different areas of the detector so that we can very easily reject information and do this on-chip filtering as close to the source as possible, because it's almost impossible to remove all the data outside and also process this at extremely fast data rates. So in some ways, we have this very unique community because we do a lot of mature simulation-based data sets, and as well as have access to decades of experimental data. And so we can do things like, data filtering and featureization, which is highly appropriate for us. Whereas there are other DOE applications, like, for example, I mentioned X-ray imaging at light sources. Over here, there are generally multiple use cases with little or no data sets. And, every week there's a completely new experiment. The beam background continuously keeps changing. So it's impossible to correlate information from even just one single frame with the previous frame. So we also want to figure out, just like how we have these type of solutions for the high energy physics detectors, we also want to figure out how to do this for the X-ray imaging detectors, where a lot of customization might be needed, but a lot of generalization is required. Okay, so that's our generally the physicist's goal, right? You would want to have a sensor and different types of sensors, ranging from sensors that are based on which could be monolithically integrated in the handle wafer of the CMOS technology, to beyond silicon sensors going into 3-5 materials, just to cope with the radiation tolerance that are needed in these environments. And then there is the signal processing layer, which is something which we have successfully in the past kind of standardized the signal processing layers for different sensors by building in some amount of customization, like, for example, changing the gain or changing the leakage current and making these tweakable from one sensor type to another sensor type. And then we are also looking at like a very near sensor computation layer, which allows us to do at source, energy efficient, high accuracy, low latency, highly parallel data processing, and then having some sort of a photonics layer, which would allow us to do both a power delivery into these compact detector systems, as well as data transmission, so that we can correlate information across different data modules. So with that, with the background, now we can kind of think about, summarizing this unique challenges that are needed for the 3D HI for DOE science mission. We need to meet the need of high mix, low volume prototyping. We need to be able to develop use-inspired chips and chiplets for DOE. Multi-project wafers are needed as a mechanism to prove out concepts which are generally high risk, high reward technology development. We also need to establish this very robust supply chain for 3D chips for science applications, and then enable the next generation of research in 3D HI, going beyond the current needs that are set by the industry, which is mainly memory and logic integration. So this is what we kind of feel are our unique challenges as well as the goals that we would like to accomplish. So with that, I would like to then think about what is of course, we all definitely need standardization, right? So what is it that we would like to standardize given the constraints that we have for these applications? So of course, we want to be able to use MPWs. So if there is a way for us to be able to use MPWs for development of these custom ASIC families for the different applications, how can we do it in such a way that like say, for example, the entire DOE community can come together and be able to create MPWs. In that case, I think some of the things that we would like to standardize is size of the chiplets, as well as the pitch of the interconnects that we would want to, like say, for example, pixelation, either the pitch connection to the sensor or the pitch, the TSV pitch, or even the face-to-face bonding pitch. Then how can we do these plug and play AI chiplets? So I just mentioned customization is needed, but can we reuse, for example, the established manufacturing pathways by keeping similar chiplets, say, for example, similar technologies, but different functionality? So AI chiplets for data compression versus filtering versus featureization, not having to, trying to tackle everything at the same time, or making it very general purpose, which kind of defeats the purpose of what we are trying to do. So can we, for example, define superpixel regions where some set of functions could be standardized? So the interface between the sensing layer and the data processing layer could be standardized. So how do we partition that? I mean, what should be partitioned? Is it purely everything to do with sensing partitioned into one layer and everything to do with AI partitioned in the other layer? And if that's the case, what's the data formatting that needs to be done from moving signals from the sensing layer to the data processing layer? So that's one set of standardizations that we are looking at. Then, of course, developing I/O protocols for the resource-constrained extreme environments. Like I mentioned previously, even with this 1 centimeter by 1 centimeter chip, we had a highly parallel system with about 1 million.
You have 1 minute remaining.
1.5 million interconnects. So how can this be standardized or semi-standardized to be able to meet our needs? And then one of the things that we have, very successfully done for hybrid pixel detectors is standardization of verification and validation protocols, because we need custom chips, but then quite a few of the IPs that are utilized in these custom chips are reusable, especially, things like slow control and how do we inject signals to be able to see if things are working correctly or not. So what are the verification and validation protocols that are needed for high turnover chiplets with, which really aims to reduce development time and making sure that these chiplets can, easily be swapped for other chiplets as and how new applications come around. And then, standardized and reusable verification IPs, but we don't want to kind of stop there, right? One of the things that we generally run into is the design team versus test team. And often the resources in the design team and test team, there's a mismatch of resources. So if there's a lot of verification and that is IPs that are already being generated for verifying, the chip functionality, how can you very quickly translate this to, actually testing the chip and validating that the chip works as well? So we have come up with some open source tools that will allow us to, translate benches that have been developed for verification, for validation. I'm almost done. Thanks for the heads up. So with that, we've come up with this MPW scheme for the science community, where we have standardized chip sizes of about 5 centimeter by 5 centimeter. If anybody wants to go larger than 5 centimeter by 5 centimeter, they have to always go in multiples of 5 centimeter by 5 centimeter. Another thing that we have found is that particularly in our case, there's a lot of mature nodes that need to be utilized, especially for the analog part of the processing of the chip. And there's a lot of mature IP that's already created as well. But we find it very difficult to convince foundries like, Global Foundries or TSMC to add TSVs as a via middle or a via first process into a technology node that they are not looking at, changing. So one of the things that we have been pushing for and trying to demonstrate is a via last process, which allows us to, be able to kind of overcome some of these issues with high mix, low volume application by,
All right, if I
utilizing.
want to, stop it now. I think this
Right.
final slide. I think I
mean this was my last slide anyway.
Thank
So that was it, and trying to create this MPW and creating specific processes for us. Thank you, and that was all for me.
Thank you for sorry, I think I had to cut you short. I think you have a lot of good content there. I think we do have like a lot of presenters here, I think for today. So we'll move forward. Hopefully, I think we have more time come to at the end. I think I have the more time, I think we can get more questions and probably extending what you want to share here.
Thanks.
So next we have Anu Ramamurthy from Microchip, who is also the colleague for the ODSA. Please go ahead, Anu.
Hold on, I'm going to try to get it into presentation mode, and I'll switch screens. Is it in presentation mode now?
Yes, you are good.
Okay, great. Now let me try, and I was going to try and get the video on. Okay, great. All right. Thank you, James, for the opportunity to be part of this this group of very smart people presenting and listening in today. I am from Microchip. I wear two hats. So putting on my OCP hat, I want to thank everyone for coming in today and putting in your time, listening, asking questions, presenting. And thank James for putting all of this together. As Javad, who is a co-lead with me on the Open Chiplet Economy, formerly called the ODSA group, we want to encourage participation. It's truly open source. It's a truly evangelistic, collaborative atmosphere. Please do join. Please contribute in the areas that you are interested in for the betterment of everyone. So today I'm going to put back my Microchip hat on. I'm going to talk a little bit about the issues to overcome for greater adoption of chiplets as I see it coming from my point of view in my workplace and what I've seen talking to people. Okay, slide needs to move. Okay, just a little bit about my company. Hopefully most of you know about Microchip, but in case you haven't, we are headquartered in Chandler, near Phoenix in Arizona, and we are a total system solutions provider. We're a pretty large company, over 23,000 employees worldwide. And as you can tell from the bulleted list there, we support a number of different solutions, starting with microcontrollers, which is probably a large part of our bread and butter, all the way up to communications, FPGA devices, data storage solutions. So we span what makes us slightly unique compared to companies focused on one or more of these areas is that we support a large number of areas. And so our interest in using technology comes from a slightly different perspective, where we try to make it work for the high end, and then we try to make it work similarly well for the low end. So we've got a different set of interests across the board, possibly compared to other companies. So we support all of these areas listed, the industrial, data center, and computing. We are in the automotive space as well, so that has a different set of reliability and requirements, which we support. Communications, we are one of the biggest suppliers of aerospace and defense. And so that puts us again into a whole different set of requirements for reliability, rad-hard, security. And then we're in the consumer appliance space with all of our microcontrollers and things. So a wide variety of applications. Using technology in each of these is slightly different, like I said, because the requirements are different, but the overlying principle or underlying principle remains the same. So I'm going to talk a little bit about, here are the advantages of chiplets, which most of us know everything about, and then go into what are the things I think can be changed or need to be solved to make adoption better, and can the EDA vendors or can help doing some of these improvements. So probably preaching to the choir here, why do we use chiplets? Why heterogeneous integration is, one is you can use existing silicon. Existing silicon proven IP is a blessing in disguise. Some of these IP are complex, especially some of the analog. It takes potentially several years as design cycles and possibly several iterations to get it right. So if you can actually get it right, and instead of being IP, it's actually hard IP, which you can set on a shelf and then reuse. I think you've put yourself in a very good position in order to get product out faster and to ensure that you have first pass success or better reliability. The second advantage, as we all know, is you optimize them in different process nodes. So we all know that digital scales really well with process node in terms of area, power, and of course performance. And we all know that sometimes the memory and the analog does not scale as well. So in order to accommodate both those needs, because most systems have a combination of both of those, you can optimize them in different process nodes. And so if you're reusing existing silicon, you're definitely reducing your R&D costs, because now you've got a development team that has finished doing the work faster, and you've got engineering resources to deploy in other places. And so what is the outcome of reusing silicon and reducing R&D cost is you've got faster development time. And a faster time to market, as we all know, especially in certain applications and categories, can make sure that you actually capture a market before anybody else and increase your share. So it means a lot of good things. And I think in a lot of applications, it's very obvious. There's no need for a lot of thought, and that's typically in the AI applications, the HPC applications. So some of the challenges that I wanted to outline and talk about are here. One is education. And what I mean by this is in a number of cases, it's very obvious what a chiplet looks like. I think in last week's presentation, Arvind from IBM talks about what is an optimized chiplet. And I think that's really interesting, because how do you disaggregate a chiplet in a smart way? I think a year or two ago, I had asked a gentleman from NVIDIA who was on a panel, how do you decide a point of disaggregation? And he said, find a place which has the smallest number of signals crossing. And that was interesting. So I find in talking to designers and architects that sometimes that is not taken into account. What seems like a good functional point of separation may not necessarily be an ideal point of disaggregation. If you ended up with thousands of signals that need to cross in a very small beachfront, now what you've done is die-to-die interfaces need to occupy a large part of silicon area to accommodate those signals, or you need to have additional logic to make it run at a faster rate. There's a lot of complications. So I think an important thing is for designers and architects to understand that you don't just take an existing chip and say, this is going to be my chiplet. There's got to be some optimization, possibly in the die-to-die interface. Similarly, when you take a large SoC and you try to disaggregate it into smart pieces, there's got to be some understanding of the implications of that point of disaggregation. What are the latency requirements at that interface? Every die-to-die interface is going to add some amount of latency. It's given if you're on SoC versus off SoC, it's going to be slightly different, and your performance and power requirements. The other important thing I feel that needs to be done is it has to be a little bit more of a holistic thought process where the architect or designer also has some interaction with the packaging person. I think that's not typically a lot of the flows where the architect sort of throws things over and it just goes down the pipeline from one piece to the other. But I think there's got to be some iterative analysis, feasibility from the packaging side too. Because if you've got thousands of lines and you need very high interconnect density, you're going to have to move to an advanced packaging. That affects your cost point too. So it's a business come design architecture piece. And if you're going to have to reuse that IP, it's important to think about, again, point of disaggregation, how will that piece of IP be used across multiple generations or across different types of products in a clever way. So one question I have is, in addition to the education required for architects, designers on how this works is, can the EDA tool vendors help with this? Is there some kind of feasibility analysis that can be done in many different ways, which connects the architect designer to the packaging guy too? So there's this direct interaction on a common platform, on a set of tools to run a multiple feasibility, to say, hey, this is a really bad idea, throw it out because you're going to need a very high density and that doesn't fit the ASP of this product. So a much more holistic outlook, if I may say, is what I was looking at in the first concern that I had.
No, I'm
the
sorry,
second
1
piece.
minute remaining.
How many minutes, James?
1 minute.
What? Okay. All right, I'm going to talk really fast now. So the second piece is the known good die and testing. And I can't harp on this enough because with the advent of micro bumps pitch going down to 20 microns, wonderful, great. Everyone's very excited and happy. How the heck do you test this stuff? Okay, you need sacrificial pads. Sacrificial pads add area. How many pads do you add? Optimum minimum number of pads, but you still want known good die. So that's an aspect that I think the probe companies need to possibly move forward to solve. The third piece is the cost. Yeah, we're trying to optimize the cost of silicon die. Very obvious with reticle busting silicon, where you divide it into small pieces, higher yield, lower cost of silicon. The cost of assembly is pretty high. So if I were to pick advanced packaging, I'm going to pay a lot per part for assembly. When is that cost going to go down? How do we re-architecture to optimize the die size, which is optimize the interface and reduce costs? And can there be tools that help predict cost and planning? So somewhat the first and the last one are tied with the education and the cost. How can these be brought together to enable us to do better? So in summary, there's great advantages. We get optimized chiplets, we get a faster time to market. We're very excited. But all of these small pieces, these are possibly the dirty details that need to be solved in order to make it successful going into heterogeneous integration and chiplets. So in summary, for microchip, we do all sorts of wonderful things. Microcontrollers, automotive, FPGAs in the data storage space, our customers, our data centers, a large part of aerospace, defense, IoT, automotive. So we want to make our products work in the heterogeneous integration space across all of these. How do we make that happen is really some of the issues that I'm working with through in my analysis at Microchip. So we're hoping that an education for architects, designers, maybe tools that EDA vendors can provide us to do better. Probe companies need some more motivation to get down to probe, smaller diameter, much denser set of microbumps. And the cost of assembly for advanced packaging just have to go down. And the hope is that with the big companies having higher volumes, reliability improving, more efficient throughput, that eventually the costs will come down. And James, I think I might have hit your 1 minute mark now.
All right, thank you, Anu. Great presentation and sharing about the benefits and challenges of the chiplet, and I'm sure many of the standard format we're able to help to tackle some of these issues. So with the next speaker, we have Puneet Gupta from UCLA. So let's hear from the education perspective how this standardization can help in this 3D-IC and chiplet development. Puneet, please go ahead and share your screen. And
so James, you want to share my own screen? Okay.
Yes.
Okay, just give me 1 second. Sorry.
While you're sharing, for all the speakers, please feel free. Please share your slides. Send email to me or any OCP members, or we can share on the OCP website. Thank you.
Can you see my screen?
Yes.
Okay, great. Thanks for the quick introduction. I'll try to keep on time. And I'll try to provide a little bit of an academic viewpoint on chiplet standardization, which seems to be the focus of this workshop. So just as a quick view of what my group at UCLA does, our focus is on system technology co-optimization. And in that context, more recently, we've been looking a lot at 2.5D and 3D integration and all the design enablement and as well as the architectural side of it. One of the things that we had taped out a year or two back, and we are still assembling it, is what we believe is the largest chiplet-based wafer scale processor system. So here the chiplets themselves were taped out in a commercial foundry. The overall system is intended to have 14,000 ARM cores, and the overall system area is roughly corresponds to a 200 millimeter wafer. So about 15,000 millimeters square. So on the right, what you see is kind of the overview of the architecture itself, right? So, and these are small chiplets, relatively small chiplets, each of them. And what we have assembled and tested so far is sort of a very reduced scale 8 chiplet system, which is what you see on kind of top right. So this is as much of a demonstrator of how large chiplet-based systems can be built at fine pitch. So this is a 2.5D system with 10 micron pitch thermal compression bonding. So the problems that we faced are very, very different from a kind of a conventional system. Here, the scale is very large. The number of bumps is massive. And then you want to still have a working system. So on the STCO side, since in the previous talk, Anu was mentioning about modeling of cost. So we actually have an open cost model. Please feel free to ping me to get a download link. It's a pretty elaborate cost model, and it is being continuously improved, which models the wafer costs, assembly costs, test costs, etc., and allows you to define an almost arbitrarily complicated 2.5D 3D system and kind of propagate its cost all the way to the end, right? So this and what we are right now working on is kind of extensions to the same model to be beyond cost and yield, but also look at things like thermal and power within the same framework. So it's so that's a quick overview. So now let me go to a couple of questions for the standardization side of things. So the first question that I think I've heard the talks last week and this week, and one of the concerns or the confusions, at least that I had, is when we're talking about these standards, which tools is the standards for? Majority of the discussion to me appeared to be focused on the tools looking like the PCB package tools. While at least from our point of view, they should really be the chip physical implementation tools. Where the kind of nature of the standard, what it should encode, etc., looks somewhat different, right? At least in my opinion, we should first focus on extending the chip physical design tool formats, for example, LEF, DEF, etc., to support packaging. right? Whether it's to describe RDL design rules, whether it's to do other things. And why I feel that's probably the right way is they scale better. And a lot of emerging substrates kind of look like CMOS silicon rather than PCBs. They're already pretty good at hierarchy management, both like timing, physical, functional, etc. And it is much more likely to be future-proof as even more advanced integration schemes like pseudo-monolithic 2.5D and 3D approaches start to emerge commercially. The second concern I had is there's obviously a lot to standardize. And we can't really boil the ocean in one shot, right? So we'll have to start with somewhere. And at least here, my personal preference would be on the physical implementation side of rules, right? Which may be kind of an easier thing to start with. Maybe the physical implementation design rules as extension to the well-known LEF library exchange format extensions. Ways to specify timing or electrical abstract. People know how to do it in context of a within chip macro already, extending the same concept to chiplets. And then some way of standardizing the description of inter-chiplet I/O. Things like how long is the reach, what is the operation of VDD, etc., etc. So some of these things we have dealt with in our own the cost modeling framework, and here that's why I'm giving a simple snippet of, for example, what an I/O description might look like, which is useful for a physical implementation tool. Okay. Now going further, one more thing that I thought is a little bit missing in the discussion is looking at larger 2.5D and 3D systems. So when I talk about 3D, more than 2+ chips stacked on each other. When I talk about 2.5D, more than neighbor-to-neighbor connections. So we will, for that, these may happen because, of course, for signaling, as I've shown, there's a small picture on the right, that you might need some sort of a feed-through channel through an existing chiplet to connect two chiplets. Right, and for this to ever work, there needs to be some sort of standardization of what feed-throughs are available and where. Right, same arguments can be made for test signals, power delivery signals, etc. Right, so there needs to be some way to standardize the description of if and where these sort of pass-through or feed-through signals or bumps are available. A much bigger problem, probably, if a future is how to standardize the test side. Is there a way to even specify what is that known good die test quality of the chiplets that you're procuring? And this is important because rework is nearly impossible for most of these advanced bonding schemes. So once you bond, you're done. And if you're talking about large systems, a small, cheap, you don't want a large, costly system to be dumped because of a small, cheap chiplet failed, right? So, and this may also aid in designing schemas for pre, mid, and post-bond testing in a whole system assembly. From an academic view, what we want is hopefully the standard can be kept fully open with hopefully at least a reference implementations of readers and writers. Again, we need to keep it extensible. Because advanced packaging is in a very, very rapid innovation mode. What we see today is not what's going to probably be available 3 to 4 years from now. And of course, to encourage collaboration, exchange of ideas, etc., is, I think, very, very important to also develop an exemplar sort of fake assembly design kit to aid sharing of tools, designs, etc., as well. So that's it for me. I'll be happy to take any questions. And as a small advertisement, I'm co-organizing a workshop on chiplet-based integration and co-design, and it will touch up on some of these ecosystem challenges as well. There are a few speakers who talked here today who will be speaking there as well, but there's a long, there are more. So if you're going to be at DAC, please plan on attending this on Sunday. Oh, it's a typo. It should be Sunday, the June 23rd, not June 2nd. Right. Thanks.
Yeah,
Thank you, Puneet. I think for very wonderful presentation, asking a great question. For quick, I think some of your question we do have like testing design kit like developing. I think on our Thursday 10 a.m. Our CDX, like feel free. I think to join that. I think we do like kind of like seeing some of the challenges what you're seeing here. I'm great. We have like kind of like have this kind of I think the command kind of like viewpoints. I think and hitting I think right in the I think the challenges I think where we need to resolve here.
So I think there were some questions from Mehdi Abdulzak.
Yeah, Mehdi, I think can you post a question in the chat? I think I'm so we short time we'll move to the next speaker, but we'll try to answer in the chat there. We come back. I think at the end I think we have more time. Sorry about that. Mehdi, like do you mind to post your question on the chat? And with that, we have a next presenter from Suhong Fong, who is from Alpha Web Summit. And Suhong, whenever you're ready, please feel free to share your screen and begin.
Okay, sure. I'll share right now. Let me know if you can see my screen.
Yes.
Okay,
Go
thank you. So we'll be talking about challenges and solutions around standardizing chiplets today. And I'll try to keep that in the time allotted. So what we're seeing right now is a rise in custom silicon solutions for chiplets today, especially around data centers. So as AI is continuing to drive performance as well as the data throughput and bandwidth, we're seeing newer generations of higher data rate needs from our IP solutions. And then we're seeing a lot of custom silicon solutions to further optimize and enhance performance for AI. Now, the computational performance that's driven by AI is seeing an increased need for higher and higher bandwidth on the network and in memory. And the power efficiency needs to be maintained while we're also seeing larger and larger workloads for LLM training. And the memory capacity and also the bandwidth needs are all increasing, while at the same time, we're seeing this latency requirement become lower for workload optimization. So what are the key challenges that we're facing? Chiplets, they cater to a diverse range of use cases, from data centers to consumer electronics, mobile, or automotive. So we need different types of design and integration strategies for different chiplets. And these chiplets, they have these multiple types of use cases from different market segmentation. And then in addition, we're to achieve standardization in chiplets is complex because it requires these common applications, use cases, as well as the protocols to ensure interop and efficiency across the different platforms and devices. So AlphaWave, we bring a set of different standard chiplets to the market today, and we're using some of our silicon proven IPs to implement that. And the common interconnect that we have is the UCIe IP for die-to-die communication amongst the chiplets. And then these are the silicon proven IP shown here that we have on our chiplets. So we use our silicon proven Ethernet as well as our PCIe and CXL IP, and we implement that over the 112 gig multi-standard SerDes PHY. We also have our HBM fine controller as well. So we implement these IPs that we have silicon proven onto our standard chiplets, and we also can implement those on customized versions or derivatives of those standard chiplets. So next I'll look at what we have in our chiplet portfolio that AlphaWave Semi offers. And in the first box, we have the IO chiplet, which we've announced in a recent PR release, and we have a PCIe Gen 6 and CXL, as well as Ethernet running over 112 gig on that, and then going over UCIe die-to-die interconnect. So that is part of our IO chiplet portfolio. And then we have the memory chiplet, which is a DDR5 memory expansion chiplet. And there are different versions of that as well that I'll talk about in the next slides. And then also there's an ARM compute chiplet, and you may have seen some recent press around that. So we are collaborating with ARM to do an ARM Neoverse compute chiplet with N-type cores. And that is enabled over UCIe as well. So let's look at the next slide. This is our custom chiplet portfolio. So we can do derivatives of what was just mentioned on the prior slide and do different versions of an IO chiplet. So for example, if we need to go to higher data rates of Gen 7, CXL4, or 224 gig. And then also we can do different versions of memory chiplets for high bandwidth to add HBM, or to have LPDDR for low power compute, edge compute, and etc. Or different types of form factor as well, standard versus advanced package. And so let me go to the next slide for the sake of time. So we're focusing on this need for standardization of the UCIe streaming protocol as opposed to a vendor specific definition. And that's what we see as a strong need today. There are many different types of chiplets out there that I just talked about, and they're for different use cases. IO chiplets or custom chiplets, there are compute chiplets or optical ones for either high density or high bandwidth memory chiplets. So there isn't really a one type fits all scenario for a standard chiplet. There will be different types for this wide array of applications, ranging from high performance compute in data centers to power efficient processing in consumer electronics. So we need to facilitate, flexible design and integration that can cater to those specific requirements. And each use case will demand different needs for power performance and connectivity, which kind of complicates the standardization process because there are so many different versions. And so also there's lots of form factors possible, from 2 to 2.5 to 3D for chiplets. So we have a extensive packaging team that implements chiplets on both standard and advanced package on silicon interposer, RDL, redistribution layer, bridge technologies, and fan out. So we've enabled both our standard and custom chiplets with our UCIe IP across all of these package technology enablers. We also see that a need to enable bump dies to be delivered between foundries. So if a customer has chiplets from a specific foundry that needs to be packaged on another foundry's package technology, we're seeing a need for joint collaboration between foundries for this enablement of bump dies going to another foundry to be packaged. So a good, robust chiplet ecosystem is going to depend heavily on this foundry collaboration, working together to create this diverse range of chiplets, based designs from different foundry process nodes with different foundry packaging types. Okay, and then in order to foster this robust chiplet ecosystem. We think there needs to be a collaborative effort among foundries and EDA tool companies to work together to develop compatible standards and manufacturing processes, as well as design rules and test methodology. So a good example of that is 3D blocks, which is a standard to address unifying the design ecosystem with different qualified EDA tools and the flows for TSMC 3D fabric. Okay, so now going to the protocol use cases. So there's a critical need for standardization, and it really involves developing common applications, use cases, especially the protocols, to ensure that chiplets from different vendors can seamlessly operate together. And then to achieve this, it really requires consensus across the industry for the different protocols, which is, it can be complex because the chiplets have so many types of use cases. So the standardization becomes a challenge. But the top row of the slide, it's showing the proprietary vendor-specific protocols through the streaming of AXI for non-coherent applications or for DDR or memory types of applications. And then there's the streaming of CHI for the coherent NOC applications. And at the bottom row of this, shows the aim to achieve a more interoperable ecosystem for chiplets, and we see CHI C2C, which ARM just talked about, or PCIe over UCIe, which is supposed to be a standardized one, or an AXI C2C, which could come from ARM as well. So these are different types of interoperable protocols that we were hoping to see more of. But as it stands, a lot of use cases where proprietary or vendor specific protocols are being used for chiplets. So yeah, we want to see the interoperable ecosystem to be spread more widely at the bottom row. And then now here's an example of our IO chiplets on the top row and our memory chiplets on the bottom row. And at the top, starting with our standard offering of the IO chiplet with 1.6 terabits per second, we enable a multi-mode of PCIe, CXL, Ethernet through our standard IO chiplet. And then also derivatives of that would be something that would be on an advanced package, or we could go to 3.2 terabits per second, offering 224 gig 6T Ethernet, or going to a Gen 7 PCIe. And then also further to go to custom IO chiplet, we could offer JESD or retimers over that IO chiplet, or other different configurations such as extra Ethernet ports to go to a custom IO chiplet. And then on the bottom row, same for memory chiplets. We can offer the memory chiplet like a DDR5 standard memory expansion off of the compute die that can be a backup, or we could go to an LP DDR5X, which would be a low power for edge compute and small form factor, or for high bandwidth HBM3. And then, we can enable all these on the different form factors of standard or advanced packaging. So this is the conclusion to the slide set, and this is a summary. So Addressing these issues is really essential for the widespread adoption and success of chiplet-based solutions. We do target the AI, ML, HPC, compute customer base. We have silicon proven IPs as well as standard and customized chiplets. And the issues that we see are that one size doesn't fit all. There's a lot of market segmentation, which means a lot of different types of chiplets that are needed in the market. And that also means different protocols. And we do see a need for the standardization of protocols, especially across that streaming enablement. And we want to see foundry collaboration for bump dies to be packaged at different foundries. And the additional references shown there are the press releases that we have recently for the ARM compute chiplet, as well as the IO chiplet that we have, the multi-protocol standardized IO chiplet.
Thank you.
Thank you.
Thank you, Soo-Hoon. I think you're right on time. And great presentation. Please feel free to share your slide, and we'll post on the online for everyone. I think I have to view and follow up. We have next presenter, Mark Ross from the SI2 organizations. So let's see, right, hear from another standard body who is also participating in the OCP CDX meeting here. Mark, you are up. Thank you.
Okay. Thank you, James. Thank you for right. Is it
thank you. Yes,
right.
We can see. Yep, go ahead.
Okay, very good. Thank you. Right, I'm Mark Rose. I've been at SI2 for almost a year now. Before that, most of my career was at Intel. I appreciate the opportunity to speak to you. I want to describe a proposal for 3D IC assembly design rules. So schematically, this picture kind of introduces what I want to talk about. It's a proposal for a CAD neutral, shared, standardized specification format that can be used in early planning and exploration. So it would be part of a 3D, it would be used, for example, within a 3D design exploration cockpit, and with all these components coming in, like interposers, chiplets themselves, the substrate, etc. Okay, so before getting into that, I want to just, for those who don't know, I want to introduce what is SI2. It stands for Silicon Integration Initiative. This is a membership-driven, not-for-profit organization, kind of a collaboration of different companies in academia, focused on standards and shareable capabilities for the semiconductor industry. Examples of what has been provided are the open access database, which supports EDA supplier or provider interoperability. The Compact Model Coalition provides a collection of standard SPICE simulation models for devices, and UPM and UPTC. UPTC is a coalition that supports and extends the IEEE 2416 Power Model standard. So SI2 also runs groups called special interest groups that look at emergent technologies or technologies where there's an important need to standardize. And one of those is the 3D IC Special Interest Group, or SIG. It has membership from design companies and EDA companies and foundries, and I said OSATs, it's actually one OSAT that's a member. So this SIG has been exploring the needs and opportunities in the 3D IC space. And so as we explored those needs, one of the things we looked at is what are the ecosystems to be aware of? What are the efforts that are being applied right now? As other speakers have said, 3D IC is a challenging design environment because it's bringing together capabilities and expertise that previously were more separate, like packaging and silicon design and system design. So there are various efforts, what I'm trying to show here at the top, that have been attempting to bridge the gap and bridge those gaps and provide ecosystems and standards to aid the design. Okay, on the left, I'm trying to show foundry-driven efforts, such as the TSMC 3D Fabric Alliance and 3D Blocks, which the previous speaker just mentioned. 3D Blocks is basically an assembly specification system, a way of describing a 3D floor plan. Samsung has something similar called 3D Code, and also Samsung has been pushing HBM standards. And then Intel is another company, as you know, that has 3D packaging technology. Intel itself is not interested in creating its own sort of 3D blocks or 3D code. But one thing Intel wants is an ADR standard, an assembly design rule standard specification capability. On the right, well, you've heard a lot in this conference about OCP and JEDEC and the chiplet exchange ecosystem, including CDX and 3DK. Then there's, of course, also the government effort, which includes the CHIP Act and you all know about NSTC and NAPMP and also previously the SHIP. So when we looked at these ecosystems, one of the conclusions we made in the SIG is that for assembly description or 3D floor plan description, that's already seems to be well covered by 3D blocks and 3D code. It didn't seem like it would make sense for SI2 to do anything there. However, the SI2 member companies did express a strong desire for standardization of the assembly design kit. And as you know, that's a large topic with many components, including rules for assembly and test and models for thermal, electrical, material, etc. And as you also know, and as I said up here, OCP already has a strong effort in 80K standardization. So SI2 doesn't want to try to replicate any such effort. Instead, what SI2 proposes doing is zeroing in on the assembly design rules portion of 80K and hopefully producing something that will fit nicely into the overall 80K that OCP is working on. So a little bit more on that. What we did was we looked at the different types of information that's going into these different ecosystems and these different attempts at standards. And we tried to see where there's overlap and where the assembly design rules would fit into that. So by the way, I should have said at the beginning, what I'm going to describe as a proposal, it's not something that SI2 has done a lot of actual work on yet, the proposal. And so this is a great time for collecting feedback. If you have any concerns or questions or whatever about what I'm going to describe, it's good timing. So anyway, on this slide, I'm just trying to show these different types of information and how they interact and such. This left circle represents a lot of the information that's part of 3D blocks, including the chip, including physical information about the chiplets themselves, like boundary and bump maps and sizes and such, and including information about interposers and package substrate and such. And then there's the chiplet description from OCP, which has some overlap in terms of information content with the 3D blocks, but it also extends more functionally. So there's the chiplet logical interface and timing model and test access and such. Then there's this whole blue circle down here, which represents the information that could belong to an ADK. Actually, I know OCP talks about ADK and MDK. I kind of combine the two into this, where it's talking about rules, and it's also talking about models, materials models, electrical, etc. And then there's the foundry PDK, where, as you know, there are different PDKs. There's not really a standard way of describing a PDK. But when it comes to silicon rules, you know, since this ADK needs to include descriptions about interposers and things like that, there's a fair amount of overlap in silicon rule description between foundry PDK and ADK. And then here's the ADR in the red circle, the chiplet placement rules, 3D stack rules, bump and bond rules, etc. Rules about the interfaces of the chiplets. So that sort of shows where this ADR could fit within this overall collection of information. Also, I show this arrow. That's because it turns out TSMC are themselves interested in having some form of ADR specification that could eventually become part of their 3D block system. Okay, so a little bit more about the assembly design rules. What are they? They're rules for chiplet designers. It's sort of two types of rules. Rules for chiplet designers to follow to enable proper assembly of the chiplets into the packages, like rules about bumps, TSVs, also chiplet sizes and aspect ratios. And then also rules for package designers to be aware of in system designers, like chiplet to chiplet spacing, stacking rules, etc. Historically, when you think about the tools, packaging tools have supported some form of assembly rules, as you would expect, but they haven't supported the type of advanced high density rules like what we're talking about needing now, you know, such as rules about silicon interposers. And there hasn't really been interoperability. And meanwhile, tools for silicon design haven't really supported assembly design rules because they've been focusing on the silicon itself, not the way the silicon gets assembled into other things, except during sign-off, because you know, during the last stages when essentially they're using foundry design rules. And likewise, there hasn't really been interoperability there historically. So what we want is a set of rules for early package exploration and analysis. As other speakers said, it's really important to make early trade-off decisions well about how you partition things, how you stack things, etc. And we want a standard way of specifying those rules, which would support mixing component suppliers and assembly and package suppliers without having to change between rule formats. So here's the specific proposal then, along with some history about how this came about. Well, I mentioned the SIG. So another part of the history is that Intel themselves came to this SI2 special interest group with a request to standardize an assembly design rule specification. And they offered their own internal ADR specification as a starting point. So Intel's ADR is a CAD neutral specification meant for doing 3D system level planning, not really meant for sign-off. And it's an evolving specification. It doesn't completely meet all those needs that I described earlier. So also, sorry?
I'm sorry, I didn't sound back on this, but you have 1 minute remaining, Mark. Thank you.
Okay, so TSMC, as I said, wants an ADR specification as part of the environment, their environment. So we reached this agreement that I'm going to show here, and this is my last slide. The agreement is that the Intel ADR spec or alternatives to it that may come up will be discussed in the 3D Blocks Committee. And it makes sense because that committee also already includes the major EDA vendors, Synopsys, Cadence, Siemens, and Ansys, and plus it'll include Intel. And then the 3D Blocks Committee will refine and evolve this specification and provide requirements to the EDA vendors and potentially requirements to SI2 itself. Meanwhile, SI2 will maintain the latest version of ADR and make it available to the SI2 members for feedback and for funneling requests to the TSMC committee. Because partly what we want to do is make sure that this doesn't wind up being TSMC specific or Intel specific. It's supposed to serve broader needs. And meanwhile, the SI2 work group associated with this may also create reference designs and utilities to help promote ADR. An example of a utility that Intel already recommended is something they call an ADR authoring tool. So I mentioned available to SI2 members. This will probably work the way that our compact model coalition works now, where during development, the standard is available to the members, but once the development is done and the standard is approved, it becomes available globally, to anybody who it could be useful for. Okay, so thank you. That's my talk.
Thank you, Mark. I think from perspective from another open standards, so we do cooperate. I think I work with Mark, I think on some of meetings here. So I think we should definitely I talk more about potential cooperation. I think and thanks for sharing. I think an overview of this. And we have the next speaker from Buchida, Irad. Irad, are you here? If you are here ready, please go ahead and share your screen.
Yep, I'm here. Just a moment.
All right.
Yeah, so I'm going to share some of our thoughts on just multi-vendor chiplet ecosystems and sort of what some of the implications of that are, and from the overall standardization and where the effort really needs to be focused moving forward. So just to briefly tell you a little bit about Buchida and what we do, and I'll refer to us in the slides as BCA. So we really specialize very heavily in delivering customized chiplet interfaces. I won't get into the details of sort of exactly how we do that. We have some of our own internal design automation sort of approaches and tools that we've built upon. But what these really let us do is deliver customized die-to-die interconnect solutions, basically with leading power performance in area and overall lowest risk across many different process technologies. We've already delivered to folks in 7 different nodes across 3 different foundries. I believe there's a question earlier on sort of what types of technologies are being addressed generally in the OCP, and it really is kind of across the board. And Buchida ourselves has been heavily involved in a number of those. So you've heard a lot, I think, already in the forum here about how things, really there's a lot of customizations, a lot of specialization that needs to be done. And what I'd like to do here is sort of just maybe remind us briefly as to why it is that things are kind of being driven that direction. And I think the key point that is really very much worth emphasizing here is that really the reason we've gone to chiplets is primarily driven by economic cost, right? And that is the ultimate driver and will continue to be the driver for chiplet adoption. Now, the sort of potentially viewed as quote unquote doom and gloom or downside of this is that the one thing that has been economically proven and sort of is out there in the real world as to why you do chiplets, right? The most well-proven and clear benefit really is manufacturing cost, right? A few speakers, sort of stated that explicitly, but much of the discussion around standardization, sort of in a sense is not so much driven by the manufacturing cost side of things. It's really much more driven by the desire to save the design cost, right? That's where sort of reuse and, repeatability and things like that, right? That's really much more of a design cost argument than it is a manufacturing cost argument. But the thing that we really, I think, have to just keep in mind here is that for the large majority of the market, and when I say majority here, I mean by dollars, not necessarily by, sort of unit counts or things of this nature. But at the end of the day, obviously the industry is driven by dollars, and that's, where a lot of the attention is going to be paid. Manufacturing costs really can't be sacrificed for design cost savings, right? Because if you have enough dollars and therefore, sort of enough volume, sort of in terms of the things that you're selling, that really means that, at the end of the day, that is going to be the dominant sort of overall cost. And so that's what you actually have to optimize for. And again, just as a reminder, the fact that manufacturing cost could be reduced by these chiplet-based sort of implementations, that's what eventually really broke the so-called monolithic march, right? The industry was on a very clear path of integration and node scaling and so on and so forth. It's really cost and manufacturing cost specifically that broke that march. So with that in mind, it's again, a lot of the discussions around standardization, I think, are implicitly driven by this let's say desire to end up in a plug and play type of market, right? And again, it's a very alluring vision, right? From a design cost perspective, you could in principle pay the NRE once, and especially as sort of a smaller company, although this is true even for larger companies, where you pay that NRE once and then you get to address like any market, right? So the thing that I wanted to sort of point out here is that, the good, but also the bad news to an extent is that, there is a working and existing example of how you build a plug and play chiplet product, and that is HBM. Now, that is the one and only example, as far as I'm aware, of such of a product. HBM is supplied by vendors who are, sort of used to competing in commodity markets. Obviously, HBM are not commodity parts, but the vendors that develop and deliver those products are used to working in commodity markets. And we have to just keep in mind that, these HBM chiplets, they're extremely tightly functionally, mechanically, electrically, thermally, so on and so forth, specified, by a standard body, right? In this case, by JEDEC. So the thing that I'm really sort of pointing towards and driving here is that if we would like to sort of, get to a stage that even approaches sort of, what a plug and play chiplet, sort of world would look like. And again, I think other speakers, sort of had similar graphs and, pointers, for example, ARM, that I really like, kind of saying, hey, look, like, we're really here and where we'd like to get is over there, with, up and to the right being implied to be good. What we really have to be thinking about is, so how do we sort of effectively define chiplets and define sort of the types of applications, that would let us actually define these things, at this level of detail, again, at the level of detail of an HBM, sort of a type of chiplet, because that's effectively what it's going to take to actually be able to put these things together and really make them work. And the other sort of implicit point here is that, if you now, without all that standardization being sort of available and sort of these definitions being there, if you try and you go say, well, hey, I'm going to try and build a chiplet that's going to address sort of many different products and many different end needs, right? Very likely you're going to end up with significant schedule, cost, power, performance, and area, and et cetera, overruns. So this is again sort of a similar sort of graph that that I think you guys have seen, where we're just sort of showing like, look, like, so what are the use cases where people are actually doing chiplets? And obviously today, single vendor, meaning you control all sides, everything that you need to do, and you really make all these definitions with, in some senses, full freedom, right? That's where we are today. The vision we'd like to get to is the plug and play market, where again, in principle, any chiplet can plug in anywhere. But the reality that I think is, emerging both today and is likely to be the case for, sort of the foreseeable future, is really that we'll have these so-called multi-vendor ecosystems where multiple vendors will actually get together. But the intent is not to say that, like, look, any chiplet can plug in anywhere. Instead, it's to say, look, we're going to really target very specific product markets and product families. And then because of that, what we can then go ahead and do is actually define what I'm going to refer to here as a socket for all of the chiplets that would go into those particular products and product families, right? Now, that's not to say that there is going to be necessarily any sharing of a given socket between one product family and a different product family, although that may turn out to actually occur. But instead, it's basically to say that, when these multi-vendor ecosystems get together, the leaders of those ecosystems will essentially say, look, for this product family, here's the functional, mechanical, and other partitionings that we believe are the best ones to actually do that will serve the needs of this specific market. We'll define each of these sockets, in that level of depth that's necessary to actually get the interoperability and get the, let's say, swappability that is the desire or the implicit goal of the plug and play market. But now you have a very concrete and defined thing you actually have to go and build to meet these requirements. And when I say that defined thing, I don't mean, sort of just like the internals and functionality and whatnot. I'm talking about even the interconnect, even, sort of the thermals and everything like this. Because again, there's a very now specific need that you have. So many of these questions about, well, like, what is the standardized way to carry, this type of traffic? Well, you don't need a standard. You just need an actual definition of a specific chiplet you are trying to build. And, then the needs and the requirements and everything like that will become much more clear. And the point here is that, once these ecosystems have defined these sockets, when they are successful, in fact, I should say the ones that will be successful, they'll serve markets with large enough volumes that it'll make it attractive for other players to come in and say, okay, I know what it is I need to do. I know what it is I need to build. I have sort of, a frame and everything to work against. but I can go now innovate specifically on, how can I make improvements in that specific sort of use case and application. So that's really, I think, kind of the primary point that I want to make here is that, at the end of the day, sort of these multi-vendor ecosystems defining specific concrete chiplet sockets for specific concrete markets with enough volume, I think that's really sort of, the biggest, let's say, hammer that we have to make progress in as an industry moving forward. But I also just wanted to give a little bit of a side note, since, we are interconnect focused, folks, and myself personally as well. Many of the discussions that we sort of end up having, sort of end up being for so let's say obvious reasons, they kind of focus in on the data standards and, effectively the challenges we have there, not just in the sort of, fine the interconnect itself, but, all of the layers around that with the protocols and the optionality and so on and so forth. Now, there's good reason for all those discussions. In fact, the reality here is even more complex than what you might, sort of first think, right? If you just say, well, it's a bunch of wires or UCIe or whatever it may happen to be. There's actually a lot of different use cases, driven by the different packaging technologies, driven by the different reach, driven by the different sort of bandwidth density requirements, driven by the cost requirements, where actually the, sort of even down at the guts of the phi, you're probably building things in a very, very different way, depending upon the specific use case that you're actually trying to target here. I won't spend time kind of, walking through the sort of the eye chart here, but this is, really just highlighting that there's a very big range of bandwidth densities, a very wide range of essentially package types and, sort of densities that we're looking at. And the real circuits inside of there, therefore, also tend to be, quite different as well. And so at the end of the day, as I said, what Blue Cheetah does is we go and we figure out with you, okay, for the particular chiplet you're trying to build, implicitly and eventually for the socket that you're working on, what is the actual interconnect you need for that? And therefore, how do you customize and deliver the best possible solution for that specific socket? That's really what we do. And, what we essentially enable is that, the interconnect is not going to be the bottleneck, right? That, we'll figure out a way to get that to be what it needs to be for that specific product. So just to quickly wrap up, and hopefully there'll be a little bit of time for questions. As I said from the very beginning, cost, whether it's manufacturing or design, is the reason that one builds chiplets. But again, manufacturing really is kind of like, in many cases, the baseline, right? That's the thing you must meet. And if you get the design cost benefit on top of that, great. But manufacturing, that's kind of the requirement. And it just turns out that the specific way in which you use a chiplet will then heavily modulate which aspects, of sort of the design you need to focus on in order to actually achieve those cost goals. So as you've heard, I think many times already, right, it's very, very unlikely that one size fits all for chiplets. Don't let the perfect be the enemy of the good, right? There's going to be many multi-vendor ecosystems that will emerge. And I think especially the early ones that are successful and sort of actually address real product use cases with sufficiently large volume, those will effectively define the specific sockets that people then need to go and actually, design for to be able to fit into those larger ecosystems. So as I said, where Blue Cheetah fits in is, we deliver customized interconnects that essentially are enabling many of these ecosystems to go after and really specify and customize the solutions that are going to fit into those particular end markets. And, we've really done work in a very broad variety of end markets. And so we see there is actually viable solutions in all of them, but it's, not really through sort of, taking the one size fits all, but it's really by doing the customization along with the definition of the sockets themselves. So that, I think I'll wrap up here. And as I said, I'm happy to take questions if we've got some time.
Yeah, thank you, Arad. I think since Arad is the last speaker, we do have a few minutes. I think I have to take in questions. Anyone have any question? Feel free to ask.
I have a question, Elad. This is Anu.
Of course.
Of course. The focus has really been on AI, HPC, and great. It's a perfect fit. There are other, when the guy from Yole presents, the analyst, he talks about, all of these high SP devices have moved to chiplets and it's perfect. But he does show maps where others will also move to chiplets eventually. How do you see that, as in the automotive non-ADAS side, in the IoT side? Because the ASP for those devices is very different from what AMD or NVIDIA does today, right? So how do you see that transition? We fixate on HPC and AI, which is great, but what about everybody else?
Yeah, no. So without obviously naming names, we have customers that are solidly what I'd call in the consumer electronics space, where cost is sort of consideration number one. And meaning like a few cents on a product is sort of make or break in some senses. And yeah, and as I was sort of hinting at here in this slide, you have to drive many of the design decisions. For us narrowly, we focus on the interconnect, and so there's a lot of things that will happen there. But even from the overall product perspective, you must drive the decisions based on meeting the needs of that particular market. And so we do see things sort of emerging and happening there. To be sort of completely blunt, I think a world where people are going to sort of go buy like 1 millimeter on a side chiplets, sort of more broadly and off the shelf, I think is probably not really going to happen, at least not in the general case, unless there's some very, very specific, sort of technological functionality that, puts you into a very, very, sort of obscure, I shouldn't say obscure, but let's say specialized or niche, process technology where, that tiny little thing enables, sort of your overall system. Great, we can do that. There's oftentimes questions about whether or not, making that a chiplet versus just its own chip, is that really, sort of saving you the overall cost in the product or not? But certainly, yeah, I mean, I think, the non-HPC AI and et cetera, there's a lot of opportunity. There's a lot of places where that really does make sense. And, I'm happy to say, I think that's actually already happening in many ways.
Oh, thank you. I appreciate your perspective a lot.
Yeah, absolutely.
Thank you again, Irad. Anyone else have any questions? Or any question for previous speakers? Would be a good time to ask.
So James, there was one question from Bill Mullen to everyone on the chat.
Yes, Bill asking about multiple speaker has mentioned about the needs for standards regarding chiplets, which information is already covered by 3D blocks, CDXML or other formats, and where are the gaps? So I think that is very good questions. I will catch short part of it. I think Matt Ross from SI2 probably share some of the information in his slide. I would say there are fragmental information. So 3D XML is really focusing on the a lot of mechanical, electrical, and IOs. There are other things not covered today, such as the materials, the testing, as Pune has pointed out, and also the assembly. I think which Matt Ross has talked about a lot. So I think which part of it, the 3D blocks also overlapping, on the mechanical side, on some of the assembly rule side. So yeah, I think that's kind of landscape today. So there are some kind of fragmental standard there. And 3D blocks traditionally, I think really focusing on the TSMC kind of assembly. So now we're not sure I have been talking to Intel, we're not sure the direction, but we do also want to do at OCP, at least we don't want to do something more open standard, which is not focusing on any foundries or any kind of particular examples. We want to be a format kind of more superset, that hopefully can be also aligned very well with the 3D blocks and other standards as well. So that's kind of what tech format. And anyone else have any other
yeah, James,
information, feel free.
I'm gonna do the former academic thing and sort of redirect the question if you don't mind.
Go ahead.
In my view and sort of what we've observed, I think there's been a lot of great work, CDXML and 3D blocks and so on and so forth. And, not to say that work is done by any stretch of imagination, but, in my view, I think the bigger challenge that I think the industry sort of, needs to start focusing on really is on just, filling the information in and saying, yeah, this is what my chiplet actually is and what it actually does and, what it needs to be and, adding in all the functionality and so on and so forth. But, picking actually real concrete design points that people can go and build off of, I think that's actually sort of the bigger next step, rather than necessarily sort of saying, well, I should, again, as I said, not to say there isn't work in the, sort of just what do we capture in the first place, but I think sort of, concrete designs and examples and, real drivers of what people should go build, in my view, is actually sort of, the big step that we need to take.
Totally, I think that made a lot of sense. I think from the industrial point of view, I think we have to work together and strive for this kind of goal and challenges, as well as other speakers mentioned earlier. Anyone else have any other tag or points? we kind of like reaching the top of our times here. Thanks for, I think I staying a bit longer. I think that like originally planned for until 10:30, but we stretch out it's 15 more minutes since we have many great speakers. We don't want to miss anyone. So we just want to share. I think I will slide here. I think so if you haven't, for a speaker, you haven't shared your slide, please send it to the email, to my emails here. I will send an email to follow up as well. We do have like other standard meeting that ongoing on every Thursdays. From 10 a.m. we have a kind of test design kits, and then like for the assembly design kit and also material design kit at the 11 a.m. on alternate with Thursdays. So with that, I think I would like to end the workshop today. We will follow up again with the information on recording outside on the OCP website. Please feel free check it out right sometime next week. Thanks again for everyone for participating and for all the great speakers. That's all.
Thanks, everyone. Hope to see you all participate more actively in many of the work streams that we have. Appreciate it. And thank you so much, James, for doing a terrific job in putting all of this together. James has been working very, very hard, believe me. So thank you very much.
Thank you, James.
Thank you.
Thanks, Anu.
Thanks, everyone.
Bye.
Yeah. Bye-bye.
Thank you. Bye.